All right, the workflow. All right. We're going to talk about basics. I'll talk in some detail about the phases, and then there are a couple questions that frequently come up, and I'll put those to rest as best I can. All right, so the actual end result of the process is a PC board. The process itself, though, doesn't actually begin with the PC board. The process relies on a workflow that actually starts way back with the schematic. And this bothers, it seems, a lot of people who are doing beginning work in PC board design sort of get annoyed by this, because they say, well, I know what I want, I know the connections I want, why can't I just open a program, draw lines between the connections I want, and say I'm done? I'll cover that in the next slide. Before that, though, I want to give you some idea of what the workflow is. It begins with schematic capture. You draw the schematic, then you associate the footprints you want to the parts you use in your schematic. Then you locate your parts, place them on the actual PC board, and then you produce files for production. These tend to be very distinct phases. Oftentimes, well, almost always, the schematic capture is a separate program from what does the layout. Sometimes the thing that maps footprints to parts is a separate program. Sometimes the thing that produces files for production is a separate program. The reason for this is that this entire workflow is designed to help minimize design errors. Design errors on PC boards can be very costly because PC boards are costly to manufacture. So that's a big reason for doing this. Another reason is that when you split up the workflow, it allows participants or team members with different responsibilities to work together. One person can be responsible for schematic design, another can be responsible for the layout, and they can actually be working in parallel. By putting this into the framework of a workflow, it also allows you to integrate the process of the PC board design with other design processes, for example, circuit design and circuit testing. You can do a certain amount of design in parallel with layout. You can also do testing as part of the workflow as well. And by that I mean things like SPICE simulations and other simulations. And the final reason is that it increases modularity and reuse of resources. That should be of resources. And since you are Bildschirm or IT people, you all know how important it is to reuse resources. So the phases: schematic capture, assigning footprints, layouts, and producing files for production. Schematic capture is actually the part of the process where you draw the schematic, where you draw a schematic. Basically what you're doing is placing parts on sheets and connecting them. Placing parts on sheets and connecting them. This is more than just an exercise in putting the graphics in the computer, because good schematic capture programs will also check to make sure all your connections are valid. This is called a design rule check or an electronic rule check. A good schematic capture program will do things like tell you have unconnected parts, or that you may have two outputs connected together. Generally, you don't want an output connected to another output, because an output may be a low impedance source. If you connect two low impedance sources together, you get all sorts of heat and other problems. Finally, the schematic capture produces what we call a net list. A net list is a text file. It's a text file that has a list of parts and where they connect. So this says I've got a part called R1. It connects my net called input to ground. Here I've got a part R2 that connects a net called output to a net named n-000000009, more or less. So this net list can be used in many places. It can be used as a basis for creating simulations. More importantly, for our purposes, it's going to be used in the actual PC board design process. So a net list, most net lists in their raw state give a list of parts and the nets to which the parts connect. The next thing you need to do is take the parts that are in your net list and associate them to footprints that you will use on the PCB. So here's a schematic, and what do I say? I have a resistor here. This is just, at this point, a resistor. It's not a quarter-watt resistor in a through-pin package. It's not a surface mount resistor in any one of a million different surface mount packages. I have not specified the package that this resistor is associated with. Because I haven't stated what package this is with, my PC board program doesn't know which footprint to use. Now this is done on purpose because this could change. This happens to be an op-amp. It's an LM741. The LM741 comes packaged in a variety of surface mount packages as well as an 8-pin DIP. The schematic doesn't embed that information. This just communicates the electrical interconnections. The mapping of the actual part I want to use is done as a separate process. Now, oftentimes, sometimes anyway, that process, that mapping can be done in the schematic capture as a separate phase in the schematic capture or somehow as annotations to parts. Sometimes it's done as a separate phase in an outside program. Sometimes that mapping of part to footprint is stored in the net list, and sometimes it's exported in another text file called a part list, a list of parts. So finally we come to laying out the PC board. Phases here are you basically import your net list, your list of parts and their connections. If your net list does not also include footprint data, you import the part list, which has your footprint data. Then you set up default design rules. Design rules are the things that say, by default, how wide are my traces? The things that connect paths, how big are they? What is my minimum clearance? That you express as a design rule. What is my placement grid? In other words, where can I place components on a grid? After that, you start putting your pins down, your parts down on the actual board. You then form the interconnections. You actually lay out physically how you want the connections to connect. That's called routing nets. Drawing, you will actually be drawing the traces, connecting the things that are supposed to be connected. And there are two ways to do this. Manually, there are also some automated rules. automated tools for doing this. That's called auto routing. You just push a button and wait a long time, and magically, boom, everything gets connected automatically. A lot of arguments about whether auto routing is a good thing or a bad thing. A lot of beginners love auto routing because it takes a lot of the detailed work that manual routing requires and makes it automatic. Old school people say manual routing is superior to auto routing because it gives you control over exactly how things should be connected. So a lot of designers, they basically use a combination. They'll use manual routing for critical connections, and then they'll use auto routing for whatever's left. Finally, when you're done auto routing, you do a test using the PC board design rule check. This test phase tells you whether all your connections are complete, whether you've got any shorts, and whether all your clearances are as you specified back here. You can also, in some advanced tools, do things like impedance modeling and some other advanced kinds of tests of the physics of your board. Finally, you're done with the design. It comes time to produce files for production. So you've got the design. You've got two options. You can make the board yourself using all sorts of really nasty chemicals. And then you make the board, then you have to drill out all the holes that you need to drill. Or you can send off your design to some third party who will manufacture the board for you. Turns out there are some fairly inexpensive resources for doing small volume production. That doing it yourself, actually doing the etching and the drilling yourself, really is hard to justify. So almost always, you will be sending the design that you created off to somebody else to manufacture. And one of my favorite people is a company called, and I have nothing to, I'm not commercially connected with these people, I'm just the satisfied customer. Alamex. They're actually in Bulgaria, very close. And they have some very, very low-cost options for doing small-scale PC board production. Single-sided boards, double-sided boards. So they're inexpensive, they do good work. Another advantage for people in Turkey is that there, at least the last I checked, there is a agreement between Bulgaria and Turkey that says PC boards can pass through customs without any taxes. So you're not going to be paying Cumruk on boards that you might send out to Alamex. There are other places, I don't remember the exact name, I've not used these people, but Batch PCB, they're well reputed. I haven't used them, but they're well reputed. They're in the United States. I believe the same agreement about Cumruk, about customs, exists between Turkey and the United States as well. I don't know of any people in Turkey doing this kind of work, and if anybody does, I would love to know. I'd love to find out, because that would be a good resource for you. The closest one I know are these people in Bulgaria, and they do good work. So, you've created your board. And now you're going to send off your files. The standard file format that board manufacturers use to specify board designs is the Gerber format. And if we have any mechanical engineers here, you may have heard of the Gerber format before. If you're not a mechanical engineer, you may not have heard of the Gerber format. Don't be scared, it's just another text file that speaks a particular language that manufacturers understand. Gerbers are used to specify the geometry of the copper layers, the geometry of the solder mask, silk screen, and so on. You may also need to send the manufacturer something called a drill file, which is a text file that specifies the drill hole sizes and locations. The need for this is vastly reduced by the fact that modern Gerbers, what we call RS-274X Gerbers, can also embed that information. So modern Gerbers that you produce have the drill information in them usually. The previous specification was RS-274D, and those generally require drill files. You may also need to produce a bill of materials, a list of the actual parts you're using in the design, and then for assembly, which we're not going to talk about, for automated assembly, you'll need to produce something called a pick and place file, which is basically a file, text file again, that tells machines that do automated part placement what parts go where. That's called a pick and place file. So that's used in assembly. This is used for accounting and other purposes. These two are actually used, these two formats are used for sending off to the manufacturer. So there are some additional phases that we didn't detail in this workflow. Most design programs, EDA suites, electronic design suites, or PC board layout programs, they'll come with a good library of parts that you use in schematics. However, at some point you're going to encounter a part that doesn't exist in the library, and you'll have to make new parts. Same for footprints. A lot of PC board design programs come with a good supply of footprints, but eventually you will be using a package for which a footprint doesn't exist, or the existing footprint doesn't match the manufacturing technology you have available. So eventually you may have to make new footprints. I'm not going to be covering these today. I've got a write-up if you want to follow how to do these things. I've got some text guides for doing that if you want to read those, but we don't have time to cover those today. There's also a process called back annotation and a corresponding one called forward annotation. I mention these because you're going to see these terms as you go forward, and just so you know what they are. Back annotation refers to taking any changes that you have made while you're laying out the design and introducing them back into the schematic. For example, you might change the number of a part, the part number. You may have to reflect that change back into the schematic. That's called back annotation. Forward annotation is the corresponding. If you make any changes to the schematic and you have to export those into the PCB design, that's called forward annotation. We won't be seeing any of these today. Now these phases, these 4 phases, they don't really automatically connect together. And this kind of bothers a lot of beginning designers. In a typical PC board layout system, they don't automatically connect together. And one of the first questions that comes up, or a frequent question that comes up, is why not? You know, when I make a change in my schematic, why doesn't it automatically propagate down to the PC board? When I make a change in my PC board, why doesn't it automatically propagate back to the schematic? Because frequently, different people are working on different phases of the design. That's one reason, or different aspects of the design. Second reason is, and this is just something that you see with experience, things can get messed up really badly pretty easily unless you take some care in doing those, in managing the different phases of the process. So turns out that the most reliable way of propagating these changes across anything other than a small design, a trivial design, is to do it manually. You're also going to see that the user interface in a lot of layout programs is just goofy. They don't adhere to user interface standards on any platform. They're just weird. This leads to a feeling, a proper sentiment on a lot of people's part that these programs are hard to use. And sad but true, yes. The user interface design for most layout programs is goofy. And there are 3 reasons for this. A couple of them are justifiable. One of them really isn't. One reason is just legacy. PC board design tools, computerized PC board design tools, have a very, very long history. They go back decades. And for that reason, there's a legacy of how things were done, how things were done before GUIs were popular, before fixed GUIs were popular. In other words, pre-Macintosh, pre-1984. A number of conventions were introduced pre-Macintosh, definitely pre-Windows. And some of those conventions are still around. They're still implemented in a lot of programs. Another issue is productivity. A lot of times interfaces are optimized based on the assumption that the person using the program is an expert. So they're designed not for an average person to walk into the program and begin using it in 3 seconds, but rather they're designed to optimize the needs of somebody who uses it, if not every day, at least very, very frequently. So a lot of the interface is based on expert user expertise. The last reason, developers of these programs frequently don't include user interface design specialists. This is a very, very technical area, and so as very, very technical people, they tend to sort of think, who needs design? At least that's my feeling, anyway. So that, my friends, is PCB design workflow. Should we do a design?
You have to go. Thank you very much.
Okay.
And for your information, we had PCB were built here in Turkey during our KiCad project.
Excellent.
With parts mounted on it. They also mounted the parts on the board.
Okay. I'll get back to you about that particular resource. And I put what I'm showing you today I have online. At that site, right there. I will add that information because I think it'll be a good resource for people.
I think I'll email it to you.
Well, thank you. And if you don't, I'll contact you. All right. Thank you.
Thank you very
Thanks
much.
for coming.
Nice talk.
Thank you.